All right. Well, we've just developed the time-independent Schrodinger equation. Let's take a look at a simple case, the case of a free particle. So in this example, I'd just like to substitute in a free particle wave function and show that it solves the time-independent Schrodinger equation. Okay? So for our free particle, the potential energy as a function of position is just a constant. It might be zero, or it might have some other value. Potential energy is only defined up to a constant. We've already found that the most appropriate wave function for a free particle looks like this. Psi of x and t is equal to a times e to the minus I kx times e to the minus I omega t. Oh, I'm sorry, that should have been a plus I kx here. There we are. Okay? Now, first of all, can you see this is in fact in the separable form because the first part of the wave function only depends on position, while the second part, e to the minus I omega t, depends only on time. Okay? So our question is, does the space part of it solve the time-independent Schrodinger equation? Well, the answer is yes. Well, here, let's see. Okay. So then little psi of x is just a e to the I kx, right? To solve this problem, we'll have to find the second derivative of this. And, well, you can do this as well as I can, right? The first derivative of psi would be ik times e to the I kx. And the second derivative would just bring down another factor of I times k, giving us minus k squared a e to the I kx. And we can just recognize this as minus k squared times the original wave function. Okay? So plugging that into the time-independent Schrodinger equation, excuse my scrawl here. Here, I'll just put an arrow. Plugging that back into the equation, we have um, minus h bar squared k squared over 2m times the second derivative of the wave function. Oh, my goodness. I made a mistake here. I apologize. Minus h bar squared over 2m times second derivative of the wave function, which is minus k squared times psi of x is equal to e minus u of x times psi of x. Okay? Here. Let's just cancel out the minus signs. So we have h bar squared k squared over 2m psi of x is equal to e minus u of x, but u of x is just u0 times psi of x. All right? Notice that psi of x cancels out here. All right? That's a good indication that the wave is a solution. It's a solution provided that the rest of the equation is true. That is, E, the energy, minus the potential energy is equal to h bar squared k squared over 2m. Okay? But notice that h bar times k, that's just the momentum of the particle. So this can be written as p squared over 2m, which is the kinetic energy. So this is true so long as E minus U0 is equal to the kinetic energy. And, well, of course, that's true. So yes, we've shown that the wave function that we've just specified here, our free particle wave function, is in fact a solution to Schrodinger's equation. Okay? Oh, what about the time-dependent part? So also, we'd like to see that psi of t, which is e to the minus I omega t, um, that solves the time-independent, the time part of Schrodinger's equation. And actually, I'll let you do that on your own, okay? All right. So we've just shown that to no one's surprise, our wave function for the free particle is a solution to the time-independent Schrodinger equation. And it's to nobody's surprise because for a free particle, the potential energy is definitely time-independent. In fact, it's just a constant. Okay, let's stop here. Um, Very good. In the last video, I'm going to show you how the time-independent Schrodinger equation can be derived from the full Schrodinger equation by separation of variables. This is a little more mathematically complex. It's good to have a look at it, but it's not central to what we're doing in our course. And you'll see this again in the full quantum mechanics course when you take that. But you should have a look at it nonetheless.